Okay, so in this video, we're going to find the integral convergence of a power series. So in my past video, we talked about the definition of a power series and saw that every power series either converges at a point or it has a radius of convergence for which all values outside of that radius convergence, integral convergence, will diverge, inside it will converge. We haven't said what will happen at the endpoints of the interval though, and we'll see it in this example. Okay, so um, the way to find the interval convergence is we want to see for what values of x this series converges. So first, this is centered at 0. So at x equals 0, this series clearly converges because all terms would be 0, regardless of the n, right? So if you want to think about what's happening in a series, just to be clarified, we had my power series written like this. So in this example, my Cn is 1 over n to the n, right? Okay, so what I need to do is find for what values of x will this series converge, and I'm going to use the ratio test. Why? Because many times the ratio test would work to find these things, to find the interval convergence. Remember, the ratio test tells us to find the limit when n goes to infinity of the absolute value of the an plus 1 term divided by the an term. And if we call that L, and if L is less than 1, that series converges. The series converges. And if the L is more than 1, the series diverges. So we're going to find this limit and play with the values of L and see what that happens. So okay, so let's go for it. So the limit when n goes to infinity of the an plus 1 term would be x to the n plus 1 divided by n plus 1, don't forget parentheses, 2 to the power of n plus 1, divided by x to the n and 2 to the n. So I'm writing at this step. In the next step, in the next example, I'll just skip that step and write it like this. So I'm going to put it like this, 2 to the n plus 1. You're always going to multiply the n plus 1 term by the reciprocal of the n term, right? So this term here goes now to the bottom, to the denominator, and this term here goes to the top, to the numerator. Correct? So by doing this, you can see that I have a few, these terms, x to the n plus 1 with x to the n, simplify. My 2 to the n plus 1 and 2 to the n also simplify. So probably use a different color for that one. So this term and that term are going to simplify. Some powers are going to cancel. So let's write that down. I get the limit when n goes to infinity of x to the power of 1 in the numerator, right? The 2's, I'm going to have an extra power of 2 in the bottom, right? And I'm going to put the absolute values here if you want. But then the n and the n plus 1 term survive, right? Now, remember again, this, what is going to infinity is the n, not the x. We're going to plug in the value of x. Think of it like once you plug in the value of x, that x is a constant. Once you plug it in, and then you take the limit when n goes to infinity. So when n goes to infinity, you can think of a little bit like this guy goes outside of the limit times this limit. I don't need the absolute values in here because these are all positive terms. So there you go. This limit here is 1, right? This part has a limit of 1 because if you remember how to do that one, this becomes, I'm not going to do this, well, I'm going to write it right here on the side. You can do 1 over 1 plus 1 over n, dividing each term by n, and then that becomes limit is 1. So this means that the limit I'm looking for, kind of like my L, is really just x over 2. Right? So this is going to converge. This is just x over 2. So the series will converge. It will be absolutely convergent, but remember that that implies convergence. The series will converge if absolute value of x over 2 is less than 1. which means that absolute value of x is less than 2, and as an interval of convergence, this means that x could be, so far we got that x is between -2 and +2, right? Okay, we're not done, because what we found so far is that the radius of convergence is 2, but I was asked to find the interval of convergence. The difference is that I don't know still if either of these endpoints could be an equal sign, if it converges at -2 or at +2. Okay, so let's check the endpoints. So I'm going to check the endpoints, and what that means is I'm going to do to check the endpoints, what I'm going to do is do when x equals -2, plug it into the series. Okay, what is a series? This was a series. It's -2 to the power of n, so it would become the sum when n equals 0 to infinity of -2 to the power of n divided by n to the n. So this really becomes n equals 0 to infinity of, I have a -2 and a 2 in the bottom. You can write like 1 over n times -2 over 2 to the n. So of course this is just -1 to the n over n. And this is the harmonic series alternating. So this is the one that converges. Correct? Remember that we saw before that this is an example where the alternating series converges when it becomes alternating, using the alternating series test. So this one converges using the alternating series test. So that way I know that in here it converges right there. My integral convergence includes equal sign on that end. Okay. So now let's look at the other endpoint. My other endpoint, it says, I'll do it over here, at x equals 2, and probably some of you already know what's going to happen. If I plug in a 2, it's going to have 2 to the n over n 2 to the n. So now it's a positive harmonic series, which diverges. So this is diverges because it's the harmonic series. Okay, so there we go. My interval convergence is what I had right here. X has to be -2. It could be equal to -2, not +2. So if you want it, the same would be interval of convergence would be including the -2, not the 2. Okay, that'll be my final answer. So this is going to happen. You take the ratio test, and you force the limit to be less than 1. Right? So like steps are, take the ratio test. Once you have expression for the limit, you force that to be less than 1. And once you get that, you find your interval convergence, kind of. You still have to check the endpoints. Step 4. Okay? Let's see if we can do another example in this same video. So my second example is determine the interval convergence for this new power series. So on this one, I'm going to do exactly the same thing. I'm going to say, using the ratio test, we know what we need to do now. We take the limit when n goes to infinity of the an plus 1 term. So I'm going to write it already like -1 to the power of n plus 1, n to the power of n plus 1, divided by n plus 1 to the power of 1/3. And I'm going to multiply by the reciprocal of the n term, which means that now the n to the 1/3 goes in the numerator, and the -1 to the power of n x to the n goes in the denominator. Okay, so do that in one step of writing that. Okay, so if I do that, now this simplifies a lot. Again, have the same idea with the x's, x to the power of n plus 1, x to the power of n, so I have s in the top. These negative ones, I really just can ignore them. It's going to be a negative 1 in the top, but it's inside the absolute value bar, so I can ignore it. So what I really just end up having is the limit when n goes to infinity of x. I can separate this like I did before. Oh no, I can't, sorry, let me put it like this. So I have n plus 1, n to the 1/3. So I can separate them like I did before and keep the x absolute value. And I have n to the 1/3 divided by n plus 1 to the 1/3. Okay, so this again goes to the power of 1. Sorry, this limit becomes 1. This is limit when n goes to infinity of, so let me put, sorry, I want to write it like this. Oh, I did it again. I want to write the power of x outside the limit, since that's not what's going to infinity in this limit, and I have just n to the 1/3. Or in fact, I can write it like this: n over n plus 1 to the 1/3. Correct. So this limit becomes 1 because n over n plus 1 is to the power of 1. Sorry, it goes to the power to the limit of 1, and to the 1/3 is still 1. So this is just absolute value of x. So okay, so this is simple. It's again centered at the origin. This will converge if the absolute value of x is less than 1. So now we know it's between negative 1 and 1. Let's check endpoints. At x equals negative 1. At x equals negative 1, what I get is, the formula is up here, so let me copy it from there. Sum when n equals 1 to infinity, negative 1 to the n, negative 1 to the n over n to the 1/3. This becomes a positive 1 over n to the 1/3. And this one diverges because, I'll give you a second to think about the reason. Yeah, because it's a p-series with p less than 1. And now let's check at the other endpoint. At the other endpoint, I get the sum of negative 1 to the n, 1. So I know, right, 1 to the n for the x, I'm not going to plug it in. I'm not going to write it n to the 1/3. And again, this is an alternating series. And I'll be careful, if it's alternating, is that the limit of the bn term goes to 0. And so using the alternating series test, to be sure, I need to check that the limit of the, when n goes to infinity of the bn's is 0, and that it's decreasing. Those two things are trivially happening for bn equals 1 over n to the 1/3. So we can use alternating series tests, so it converges. So this is backwards. For this example, the interval of convergence is including the 1, but not the negative 1. So from negative 1 to positive 1, close right there. The radius of convergence is 1, and this is the interval convergence.